Okay, so step one is relatively 1.1 is relatively simple. It's just a binary binary star system,
Mm-hmm.
and you probably remember you can even
Reduce
yeah,
mass.
you can even do a reduced mass system. Okay, so um, we'll just do the normal approach. The gravitational force is proportional to the centripetal acceleration, which has the omega. This can also be done through the reduced two-body system. So in that case, we will pretend maybe the big M is motionless. It creates this gravitational acceleration, but that's exactly the centripetal acceleration for the reduced mass. Okay. So both solutions are really the same because O is the center of mass. Okay. I think I need to copy this picture. In astrophysics, mu is called a Lagrange point. When you place a object at Lagrange point, the the object and the masses forming the Lagrange point, they will form a stable triangle. Between the Earth Moon system, the Earth and the Earth and the Moon also creates Lagrange points. I think there are five Lagrange points for the Earth Moon system. That's typically where if you want to, if you want to launch something that can remain motionless relative to the Earth and the Moon, that's where you would put it. Now, some of the Lagrange points are stable. Some of the Lagrange points are unstable. So, this is so in this question, we are trying to, we're trying to work on that aspect of the setup.
So the sum of the two gravitational forces should be radial, essentially, right?
That's right. Yeah, towards the center of mass. let's label a bunch of things. Okay. So the net force acting on mu must be pointing at O, as you mentioned. And the tangential component must cancel out. Okay. Then what we'll do is we will try to get rid of the um, one of the masses. So we'll plug in the second equation into the first equation. Um,
We also know x1 over x2 times sine theta 1 over sine theta 2 is capital R over little r. So I guess we could eliminate the sine thetas in the second equation.
yeah, that's right. Okay, so we'll use a summation angle identity. And then we plug in the omega squared. From the first question. And the law of sine indicates, I think we should label these angles as well. Alpha 1, alpha 2. Sine alpha 1 over x is sine theta 1 over big R. Therefore, um, we also have sine theta 1 plus theta 2 over R plus small r, and that's equal to sine alpha 1 over x. So they're all the same. And the goal is to relate these two.
Isn't sine alpha 1 over x2 in the second equation on the bottom?
Well, I want to, you see, I want to use the triangle on the left.
But how do you get the
Mhm.
theta 1 plus theta 2?
Then I'm using the bigger one.
So then shouldn't it be across from a alpha 1 is then across from x2, right?
Oh, yeah, yeah, yeah. Thank you. Yes. Then we cannot say that yet. So instead, we have to do a division from here. Um, I guess one can also do a plug-in, maybe, since at this point we know sine alpha 1 is sine theta 1 times x over r. That's divided by x2. So now we can use that. So now I'm plugging in everything back into the dynamics equation. Okay. We can cancel a bunch of stuff. G small m mu sin theta 1 x. Okay. Oh, I guess we cannot cancel small m. So G mu sin theta 1 x. Then we have m um, r plus small r x2 cubed equals big M plus small m over r plus small r cubed. Okay, units check out, so it should be fine. Okay, therefore x2 is, well, x2 cubed is equal to m r plus small r to the fourth over big M plus small m times um, big M plus small m times r. So that's the distance to small m. That's the distance to small m without without redo the problem. Symmetry should tell you the other one must be this, right?
Yep.
Now for x we can plug in uh, we should be able to plug in for x. I think we have to solve for one of the angles using law of cosine, and then just you maybe use law of cosine again.
I think you could also use Stewart's theorem,
What's that?
which is like if you have the
Mm,
Chavian, then the sum of capital R times little r
mm-hmm.
times capital R plus little r. Um, if you take that, and then you add x squared times capital R plus little r, then you get um, x1 squared times little r plus x2 squared times capital R.
Oh,
So yeah, it's more direct.
okay. Yeah, so just find x at this point. So that's good. Let's go on. Now there's a special case. So it means this. So question 1.3 basically tells you this point must be a stable Lagrangian point
Yeah.
because it performs a simple harmonic motion. Okay. Now there are a couple of ways. There are two ways to go from here to find this omega. The first way is to set up conservation of energy and take a time derivative on this. The second way, the second way is to basically look at the dynamics equation and solve for a equilibrium solution, which we did. Okay, and then introduce a small disturbance and then linearize the disturbance. Okay. So we'll try both ways. They're both pretty advanced. So the energy of the infinitesimal mass. Okay, the energy of the infinitesimal mass is has three essentially three terms. gravitational potential energy from the big mass, gravitational potential energy from the small mass, and finally the kinetic energy of the small mass. Okay. Now, the problem tells us the disturbance happens along the radial direction. So the speed of the point mass must have two components, a tangential speed and a radial speed. The tangential speed is simply x omega, and the radial speed is dx dt squared. Okay. So that's a general expression for the energy of the point mass. We should also use the fact big M is equal to small m. So it should be a isosceles. Okay. I guess at this point it would be also useful to solve, plug in the numbers and solve for one of the height here. Okay. And that will be m 2r to the fourth 2m r, and that's equal to 8 r cubed, and x must equal 2r. Interesting. It's a isosceles. It's an equilateral triangle. Okay. So let's draw everything again. So let's also simplify our total energy. It will be twice gm mu over x over x1 plus 1/2 mu x squared omega squared plus dx dt. The angular momentum of the point mass, which is mu um, x squared, I omega squared. I omega is mu x squared times omega. That's a conserved quantity because there's no external torque as the object is oscillating. Okay, so now we should be able to differentiate our energy as a function of time, but of course that's zero. It's a conservation of energy, and we have negative 2 gm mu x1 squared and x1 dot plus 1/2 mu um, here both x and omega are changing, so we have to use product rule. 2x x dot omega squared x squared 2 omega omega dot um, we will write that x dot squared 2x dot x double dot. Okay, you see our goal is to somehow write, our goal is to get to that point. That's the master equation for simple harmonic motion. So somehow we need to get to that point. We also need to take a derivative of the angular momentum because that will give us a relationship between omega dot and x dot, which we substitute into the derivative of the energy equation. So we can get rid of all the omega dot. As usual, our goal is to get rid of all the x dot actually. So we need to do a product rule again. 2x x dot omega plus mu x plus x squared, and that's equal to 0. Sorry, x squared omega dot, that's equal to 0. Therefore omega dot is equal to negative 2 omega over x dot.
So are we gonna solve for x dot, or so are we gonna substitute omega dot or x dot?
We are trying to eliminate x dot.
Okay.
We want to cancel x dot out from every term,
Okay.
and at the end we should be left with a formula where x double dot is proportional to x. That's basically the spring object relationship, right?
Yeah. Yeah.
And it's getting there because at this point we can see, yeah, every term has a x dot, so that will cancel out. So the remaining thing is just to get rid of x1 dot, replace x1 dot. To do that, we will do dx1 dx x dot. if we change x slightly, how does dx change? Well, for that one, we will say x1 is equal to x times uh, x times cosecant alpha, right? X1 is x over sine alpha, therefore x1 is x cosecant alpha. Um, you might also want to say x1 squared is x squared plus r squared. That's also okay. I think that might be easier. You do an implicit differentiation. 2x1 x1 dot is 2x x dot. But it will get to the same point. It's just x1 dot is x dot cosecant alpha. Okay, therefore x1 dot is x over x1 x dot. So now we have every element. So we put all the elements back into the energy derivative. Omega dot negative 2 omega x x dot 2x dot x double dot. Okay. So now everyone has an x dot. We can then get rid of x dot, and then we see there is a relationship. There's a linear relationship between x double dot and x, and that's exactly what we're looking for. Let's also get rid of the mu, the x dot. Okay. I think we can also get rid of the 2. They all have a 2, so get rid of the 2. Um, okay. So collect all the terms. 2gm x1 cubed x plus x omega squared minus 2. I think we can actually cancel these two guys out as well. We'll be left with 1 x omega squared plus x double dot therefore x double dot is negative 2gm x1 squared, sorry, x1 cubed, minus omega squared x. Okay. Are the units okay? The units are okay. Yeah. So that means it's probably correct. Maybe the coefficients are off by 1 or 2, but it should be correct. And it's quite interesting. Um, this is the oscillation angular frequency. I think we see that it actually might not be stable. It depends on the values. So I think it should be useful to check if they're actually stable. Um, okay, so omega squared is very early on G2M over 2R cubed. G2M over 2R cubed. That's 1 fourth GM R cubed, and 2GM x1 cubed is 2GM root, no, 2R cubed. Uh, wait, so there must be something wrong then, because we're getting they're equal. Is there a 2 somewhere that's missing?
But x1 is not going to be 2r.
Hmm?
Wait, what x1, because it changes, right? As you,
Well,
or it's approximately the same, I guess. Yeah.
yeah, x1 is approximately the same. Unless I think we may have to, okay. Everything else seems okay. No calculation error. We may have to rewrite x1. X1 squared is x squared plus r squared, which is x naught plus delta squared plus r squared. Therefore, um, it's equal to r, just expand everything, x naught, 2x naught delta squared, r squared, take r squared out, it becomes x naught squared, r squared, 2x naught delta over r, delta squared over r squared, ignore that, so it's just r squared
I think
x.
you're missing a factor of r in the second term.
Uh, that's right, yeah. 2x naught over r delta. So that shouldn't matter. Then the oscillation one is gm, 2gm over r squared, no, r cubed times this guy.
copy r squared again,
Yeah.
and also in the above equation.
Yeah. Very good.
So now we use binomial theorem.
hmm
So it's the same as the, oh, it's the same.
So,
Okay.
so I think we want to take the x naught out, right?
Yeah.
Want to take the x naught out.
Or
Um,
x naught squared over r squared.
yeah, x naught squared. Yeah, we want to take the x naught squared r squared out, and that just becomes x naught cubed on the outside. And then binomial will give us 1 minus 3 over 2 r over x naught delta. Uh, no, delta over x naught. We didn't make any approximations before this point, right? Everything else was exactly calculated. Um, 2gm x1 squared x1 squared. These term actually cancel out because 2gm over x naught squared is exactly omega squared. Oh wait, it's not. Sorry, it's not. It's not because x naught is only x naught. Yeah, so we need to do this 2gm over x naught cubed is 2gm over root 3r squared cubed. So 2 3 root 3 gm over r cubed. but omega squared is 1/4 gm over r squared, gm over r cubed, which means we can we don't have to worry about the linear term. The linear term doesn't really matter.
Isn't there
Hmm.
a missing factor of 2 in the second square next to the delta?
Sorry, where is it?
Because you had 2x naught over r squared delta. When you expand, it should be 3 halves 2 delta over x zero.
Uh-huh, okay. So over here, you're saying.
Yeah,
Okay.
yeah,
Yep. Thank you. But that doesn't matter now.
yeah. I did.
Because we basically found out the oscillation frequency relates to the original frequency.
Mhm.
So that's actually very tricky without if you know if we do not consider the changing length in x1, they are essentially the same. That tiny change in length creates this oscillation. Let me just double check. Okay. GM GM, that's a quarter. That's 2R. So that's also a quarter. Yeah. Okay. Um, okay, so let's look at the second way. The second way, we go back to the dynamics equation. We look at the radial direction force balance, this one. Maybe a bit more simplified. Maybe this one. I think this is better. Okay. Um,
So here you have to use torques for the angular momentum calculation.
well, you see, that's the equilibrium equation,
Oh, so you still have to
right?
factor in your rate.
What yes, well, what we want to do is we first we should convert this into a function of x, and then we introduce a small perturbation in x, and then we linearize that equation. So uh, okay, actually, because we know it's a equilateral triangle, this makes everything so much simpler. Um, we know that G m mu over um, Gm mu over x2 or x1 squared, and there are twice of them, that's equal to mu x omega squared. So let's rewrite this slightly, getting rid of the mu, and also maybe group everything over here. And then we also use the fact x2 squared is x squared plus r squared. That's that's good. Then what we do is we introduce the disturbance.
Where's the square root of 3?
Hmm?
The square root of 3, do you
There's
still...
a square root
Yeah.
of 3. Yeah, thank you. By the way, this is also a standard technique, finding angular frequency. Other than other than establishing the dynamics equation, you know, exactly, this can also work. And conservation of angular momentum still, um, still implies the same thing. Just copy that down here. Did I do the derivative of angular momentum correctly? 2x dot omega x squared. Yeah, so that's okay. Okay, so this angular momentum is equal to mu x plus epsilon squared. Let's call that omega prime. So that's our two equation. Um, what we what we can do from here is to again establish a relationship where epsilon double dot is proportional to epsilon. But that process is actually very similar to what just happened above. Um, you see, in a sense, the previous equation is down in the in the binary star reference frame, and this approach is down uh, essentially in the frame attached to the infinitesimal mass. The This small disturbance is relative to the equilibrium position of mu. Okay. Okay, so let's continue. By the way, you can still do the traditional approach. The traditional approach would just be uh, imagining you have a slightly, let me exaggerate this. You have a slightly different position because we know, you see, we know a fact. We know that at the equilibrium position, x double dot is 0 in the radial direction, may be relative to the inertial frame. Well, sorry, the non-inertial frame. And that quantity is essentially our epsilon, right? Um, so you can still set up an equation where you say F net equals in the radial direction equals MA R, uh, again relative to the non-inertial frame. So here you want to add that fictitious force, but that fictitious force is exactly negative ma centripetal acceleration. That can also work. In fact, I think their fundamental ideas are all pretty much the same. It's just we're introducing a differential change and then study under the condition there's a differential change how the acceleration from that differential change relates to the differential change. So yeah, so in this case we're looking for that relationship, the omega squared. Okay, so let's continue. I think we need to continue.
Wait, they say that the sides are 5 million kilometers long. So the red line.
Yeah. The Earth's radius is 6,000 kilometers. So the distance between the satellite is roughly maybe 1,000 times the radius of the Earth. And the Earth Moon distance is 60 times the Earth's radius. So these are pretty large construct. That's actually a trivial question, 1.4. because we already know essentially it's geometry. We have a equilateral triangle inscribed in a circle, right? We just need to find the radius essentially. Um, Too many R's. Too many R's. Let's call this L. And that's big L. Big L is 5 million kilometers. Small L is um, 1/3 of root 3L, right?
Yep.
And the tangential speed um, is omega small l, which is 2 pi over period times small l. And then we need to find relative speed, which we need to do a bit of geometry. So if we move one of the vectors here, um, we see we're trying to do something like this. So that's that one, that's that one. We move the first one over here, and that's their relative speed. So again, that delta V is just twice Vt times root 3 over 2. That's the relative speed between them. Okay, then we plug in everything. 2 pi over t times L, which is root 3 over 3 capital L times root 3 over 2. All the root 3 cancels out. One of the 2 cancels out. So it's just 2 pi capital L over t. Okay, so if we plug in the numbers, 5 times 10 to the 6 over 365, 86400. How much would that be? That's 10 to the that's 10 that's 10 to the negative 7. But this is kilometers, so about 996 meters per second. Yeah. So the last question is actually trivial, very simple question. I think the most difficult part, I guess the most difficult part is finding the simple, the frequency of the simple harmonic motion. Other than that, it was a very interesting problem.
So these satellites, in the last section, I was a bit confused about at what radius they're traveling at. Like, because if they are separated by such a large distance, how can they be in the same orbit as Earth? Like they
Mm,
depict it
mm.
like that, but I think do they just mean like an angularly they're like trailing or something?
Well, the Earth sound distance is tremendous. The Earth sound distance, that's much, much bigger than 5 million kilometers.
Mm-hmm.
So, from the sound's perspective, they're still basically a point.
Uh,
1 AU is this much. That's 1 AU.
in kilometers?
In meters.
Okay.
5 million kilometers is 5 times 10 to the ninth. Um, how much is that? 1.44 times 10 to the 11th.
Okay.
Mhm. So that's like a hundred times bigger
Yeah.
than these guys. Okay, it's good. Start drawing a picture. Okay. R naught is much much bigger than T. And we're given the surface tension potential energy is gamma dA. So in question one, we need to find a ratio between rho I Ti, rho A Ta. In terms of gamma, the surface tension Pa, the air pressure, and R naught, the radius. Also, gamma is not a function of temperature, and so for the first part, it's really just dynamics. We must have a force balance. The standard way handling that is is to imagine there's a hemispherical cut. There's a hemispherical cut, and the hemispherical cut, this is also related to one of the F equals ma problems. Along the hemispherical cut, there's a surface tension 2 pi r naught gamma, but the soap bubble has two faces, so you multiply that surface tension um, by 2, and that surface tension force is responsible for keeping the bubble in place because there's a pressure difference um, between the inside and the outside. The pressure inside must be bigger than the pressure outside, otherwise it will collapse. And Gauss's law tells you that pressure difference essentially works on the cross-sectional area. Okay, so that's that's dynamics. The second equation comes from ideal gas law. The pressure inside, because we need the pressure inside to solve the dynamics equation. The pressure inside is PV equals nRT.
Mm-hmm.
And the the number of mole is mass over molar mass. Okay, and the mass over volume. So now we use the relationship mass over volume is density. Okay. Okay. So then we, because the outside, on the outside the same thing happens. PA is equal to rho A over molar mass of air, but really it's the same stuff, air. Okay, 4 pi r o gamma equals, so it becomes a density difference, rho I minus rho A r, oh, there's also temperature difference, so Ti minus rho A Ta. Okay, that's where the ratio is coming from. R over molar mass times pi r naught squared. Okay, r naught is radius, r is ideal gas constant. Okay, and we can also see that rho I Ti equals Pi capital M over R. Rho A Ta equals Pa capital M over R. We divide them. That's the ratio they were asking. Which is Pi over Pa. Okay.
Yeah.
But then we can also solve 2.2 at this point, because all we need to do is divide this equation up here by rho A Ta.
Oh, for 2.1, you have to express it in terms of PA, R naught, and gamma. So I think you have to
Mm.
convert
Oh,
PI in terms of gamma and R.
okay. So for that, we need to go back to the original dynamics equation, the very first one, and then we 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 divide this equation by PA. It becomes 4 pi r naught gamma PA equals pi over PA minus 1 pi r naught squared. So pi over PA is 4 gamma PA r naught plus 1. So that's what this is. 1 plus 4 gamma over PA r naught. Yeah. So that's the variables they were looking for. So for the numerical value, uh, we can just plug in the numbers. I think if we already have this expression, we can just plug in um, 4 gamma PA r naught, which is 4 times 0.025 over 1.1013 times 10 to the fifth times 0.01. Okay?
Yep.
And this number is, how much is it? Four times 0.025 divided by 1.013 divided by 0.01, 9.8, 9.8, 9.88 times 10 to the negative 5. It's a very small number. Okay, the bubble is initially formed with warmer air inside. Find the minimum numerical value such that the bubble can float in still air. So basically, the density has to, there has to be certain density relationship. The average density of the bubble must equal the density of the air. So the average density of the bubble must be the mass of the air inside, the mass of the bubble divided by the total volume. This has to happen. Now the mass of the air inside is density times the air inside times the volume. The mass of the bubble is density of the bubble times 4 pi r naught squared thickness divided by V. So that is just V rho I. Okay, that is just rho I, and that's 4 over 3. So 3 rho B T over R naught. Um, and then we need to relate rho I to temperature. we need to relate rho I to temperature. So we have that we have that first solution where rho I Ti rho A Ta equals 1 plus 4 gamma Pa rho R naught. Therefore, rho I is uh, well, I think it's easier. I think it would be easier to solve for rho I first and then just plug in everything else into the second equation. So solve for the necessary rho I, which is rho A minus 3 rho BT over R naught, and then plug that into um, the first relationship. Okay. After the bubble is formed for a while, it will be in thermal equilibrium with the surrounding. This bubble in still air will naturally fall towards the ground. That has to happen. As long as the density of bubble is bigger than the density of air, which is most likely to be the case. Find the minimum velocity of a updraft that will keep the bubble from falling at thermal equilibrium. So that's the drag force. So the dynamics condition then for this one must be the drag force equals average density times volume times g. That must be the solution. The drag force is 4 pi eta r naught mu. The average density we already found to be rho A 4 over 3 pi r naught cubed g. Okay, so it's relatively trivial. Okay. Although I think it doesn't want the rho A for the it want the it want the case where rho bar is less than rho A. So we should still use rho bar then. Then we need to have a balance. The buoyancy force plus the drag. The buoyancy force plus the drag is equal to the weight. The buoyancy force plus the drag is the weight. Yeah, so it would be rho A 4 over 3 pi r naught cubed g 4 pi eta r naught u. That's equal to the average density, which is rho I uh, plus 3 rho bt over r naught Vg, but we recognize at thermal equilibrium rho I will be rho A, or should that be the case? No, that's not the case because there is surface tension still.
which has to support the
Mm.
difference in pressures, right?
So yeah, so the density will actually be slightly bigger than the yeah. So we've again from that first relationship, we see it's slightly bigger. It's like 10 to the negative fifth time bigger. So it would be rho A times, this for gamma PAR naught plus 3 rho BT over R naught VG. Okay. Yeah, it's actually quite tedious for the actual numerical calculation. Okay, 2.6. If this spherical bubble is now electrified uniformly with a total charge Q, find an equation describing the new radius in terms of the old one and the emissivity of free space. Because the charge will repel themselves, which creates uh, which creates
Could you use potential energy here?
yep, positive potential energy.
Also, you want to have the
Mm,
derivative with respect to the radius be 0, right?
yeah, yeah. So we want to minimize the electric potential energy and the surface tension potential energy, the sum of that. Oh, they're also telling us in all the equations below you can neglect the surface tension terms because gamma adds very little to the accuracy of the result from the numerical calculation. So the physics consideration here is to um, imagine you see the charges, they repel each other. So symmetry tells us the repulsion must be radial, perpendicular to the surface, which is equivalent to an extra pressure. We want to approach this by treating the repulsive interaction as a extra pressure from the inside pushing towards the outside.
But then how could you
Mm.
also have inside pushing outside in terms of the gas? Because then it would just keep going.
Right. I think that's why the problem tells us we don't need to worry about the. I think that's why it doesn't. Oh, just to answer your question, the air density within the bubble will become smaller and smaller.
Oh yeah. Okay.
Yeah, that because that's an increase in volume. So it, because we can ignore the gamma effect, essentially we are writing down this equation. The gamma effect is still there. The surface tension effect is still there. It's just that we are starting from some kind of equilibrium position. So we're really looking at a change in radius. Okay, so first we have that. The tricky part is how to find the pressure due to the repulsion.
Could you do like
Mm,
the pressure times the
mm,
like the you could do an equivalent energy like a PV kind of work and see how the potential energy
mm.
changes.
Yeah, that's possible. Then you need to find the self electric potential energy. That's not easy, but it can be done. One way for you to accomplish that is to start with a tiny patch, and then you build up all these little rings of surface. But I think it's easier. It's better to just uh, because we're trying to do pressure, we can just say it's force over area. Force over area. Why is there a force? Because all the other charge,
Are acting on that one
they're
spot.
yeah, they're all acting on that spot, which has a delta Q amount of charge proportional to delta A. So that delta A will cancel out automatically. Um, and that force is delta Q times the electric field which must be perpendicular here. Okay, so it must be sigma E. Sigma being the surface charge density. R1. I think they're using 1. Okay. To find the electric field, we can use Gauss's law. We can draw an imaginary cylinder. Again, that's from the symmetry of the problem.
And this is
Mm.
it's gonna be there's electric field in both directions.
Mm.
You're right. Actually, wait, inside there's no electric field, but outside there is. Or
Yeah. Is there electric field inside? Or maybe not.
there's
There shouldn't be, right?
because you can
Yeah.
surround it by charge. You can do a Gauss's law
Yeah,
argument for that as well.
that's right. We can do another one, but it has no charge and it's symmetric. So let's do that. By the way, this is a common tricky part about this calculation, okay? You see this E, if you think about it carefully, this E is um, I'm going to imagine they're all positive charge, okay? This E is due to all charges, because we're using symmetry, including the ones at delta A. Does that seem reasonable when we do this calculation right here? This electric field is due to all the charges. But the thing is, when we do force calculation, we cannot use this E. So really I should do E prime. What I use in F equals QE is E field due to
The rest of the charges.
the rest of the charges, exactly. The rest, excluding what is at delta A. So I need to look at delta A again, and I need to draw another Gaussian surface. Okay, but this time it will create delta E in both direction, because I'm looking at something alone. Okay, and that's also relatively easy. Delta E is sigma over 2E naught, right? Is that okay?
Yeah. Okay, yeah, that makes sense. It's just a plane with two sides of charge, so it's
That's right. It's just a plane. Uh, well, it's really a small portion of an infinite plane.
yeah.
Because we're looking at. By the way, we're looking at essentially right at the charge. As long as the distance, as long as the height is much, much smaller than the size of the patch, you can do that. As long as we're very looking very closely at what's happening at the patch, we're okay. All right. Therefore, what is E? E is E prime minus delta E. Because the one that's pointing into the center doesn't matter, it gets cancelled out. What really matters is the one that points outwards. So basically, you're taking away the component that's pointing out. What's left is what everyone else gives to this little patch. Therefore, it's sigma squared over 2 epsilon naught. Oh, did I drop my delta QE? No, I didn't. That's okay. So now we can complete the calculation. Everything is a function of V1. Okay, so let's copy this down again. Pressure inside plus pressure due to electric field is pressure outside, and pressure inside is um, if this spherical bubble is not electrified, so pi VO over V1 plus sigma squared over 2 epsilon naught is equal to PA. If we are to ignore the yeah, so if we ignore the gamma effect, then we can just say pi equals PA. Ignore gamma, ignore the effect of gamma. PA V naught over V1 plus sigma squared to epsilon naught is PA. But by the way, of course, you can also do a direct integration, right? You set up the rings, you check their component, you check the component, you sum everything up. That's another way. You will see it's exactly the same. Also, also there's a common type of question. That is, if you have a parallel plate, you have a parallel plate, okay, and what's the force between them? What is the electric force acting on the parallel plate? Again, the you already know the E is sigma over epsilon naught. Um, by the way, you do not want to say the force is sigma A, sigma over epsilon naught, because that electric field is actually created by both of them, that E.
Yeah.
So
But
yeah,
there's
yeah, exactly,
individual ones.
exactly. You have to divide E by two. It's really the same spirit. Okay. So let's look at 2.7. Assume that the total charge is not too large and the bubble only experiences a small increase in its radius. Okay, so that's just binomial expansion where you actually solve this equation. So we'll just write R naught cubed R 1 cubed plus sigma is q over 4 pi r1 squared 1 over 2 epsilon naught equals pa. So that is roughly 1 minus 3 um, delta over r naught squared over r1 cubed. R1 is R naught plus delta. So that's a linear term. No, no, that's just delta over R naught. And over here,
Here there's no R naught term, so
mm, well, we
you can
still have,
always solve.
yeah, we still have R naught from the R1 squared,
Uh,
right? So 1 minus 4 times this time delta over R naught equals PA.
don't you have to square Q?
Yeah, we need to square everything here. Q over and epsilon naught. So put that in here. Then the delta can be solved. Sounds good?
Yep.
Okay. And the final question is again, average density must be the density of air. Um, so now we we have um, the density will be smaller due to, I think it must be this. That's the rho I term plus the same thing 3 rho b o 3 rho bt over r naught. And of course that delta is related to the charge.
Yep.
Okay, yeah. So very interesting question. I think that's it.